There we go. Okay. Hello, everyone. Okay, we're going to begin a new chapter today. This will be chapter 7. And I'll share my screen in just a moment here. There we go. Okay, wait a minute for that to load. Okay. And okay. Okay. I don't see anyone else waiting to join, so I'm going to go ahead and share my screen. Okay, I'll send out an email, but I have posted a new assignment on sapling for stereochemistry. Okay, that will also be due Friday. Okay, there we go. Okay, haloalkanes. Haloalkanes are also called alkyl halides, and they're characterized as compounds containing a halogen atom covalently bonded to a sp3 or tetrahedral carbon. Okay, they're distinctly different from compounds that have a halogen bonded to an alkene or an aromatic ring. Okay, those will react very differently. In fact, we'll have a whole different chapter on aromatic compounds. Okay, haloalkanes or alkyl halides. Okay, a lot of the naming rules will still apply. Okay, in fact, just about all of them. We locate the parent alkane. We'll number the parent chain to give the substituent encountered first the lower number. And we'll show halogen substituents by these prefixes. And we'll list them in alphabetical order with other substituents. All right, the prefixes are fluoro, chloro, bromo, and iodo. Okay, not the names of the elements or the names of the anions, but we'll use these prefixes. Right, the symbols Okay, the symbols are F, Cl, Br, and I. All right, notice that fluorine is just F. Okay, there's a very common mistake to list fluorine as Fl. Okay, so not Fl. Okay, there's actually another element with the symbol Fl. It's not on this periodic table that's in the room. It was a recently discovered element. It's number 114 called fluvonium. So fluorine is not Fl, it's just F. All right, notice also the spelling. Okay, there's a U in there. And the mnemonic here is that you owe it to yourself to spell this correctly. Okay, chloro has an H, don't forget the H. Chloro, bromo, and iodine. Right, so this one down in the lower left, okay, we'd start numbering from the right because the methyl is a substituent that's encountered first. Okay, so it's 3-bromo, 2-methyl pentane. Okay, we list the substituents alphabetically. In the middle compound, the alkene takes priority. And that's the highest priority group, and that's automatically between carbons 1 and 2. Okay, the halogen will fall where it may. Okay, so that means the bromine is on carbon number 4. Okay, we want to go in the direction such that we give the bromine the lowest possible number. So this is 4-bromocyclohexene. It's understood the double bonds between 1 and 2, so we didn't locate that. Okay, we haven't really talked much about naming alcohols. We'll have another chapter coming up about alcohols, but alcohols will end at OL. The alcohol takes priority in this case over the halogen. Halogens are way down at the bottom as far as priority in naming. Okay, so alcohol takes priority, so that's automatically on number 1. Okay, so the chlorine is on number 2. All right, so this is 2-chlorocyclohexanol, and this is chiral, so the configuration at carbon number 1 is S, and that at 2 is also S. Okay, there's several polyhaloalkanes, which are common solvents. I suspect you've probably used dichloromethane or methylene chloride in lab, is that right? Okay. Dichloromethane is the IUPAC, and then methylene chloride is the common name, but it's widely known in the United States under that name. CH370 is trichloromethane, commonly known as chloroform. Also a common solvent. A long time ago, it was used as an inhalation anesthetic, but it was actually very dangerous and carcinogenic, so it's no longer used for that purpose. Okay, this next one, commonly it's called 111 IUPAC, it's 111 trichloroethane. Commonly it's called methylchloroform. And this last one, tetrachloroethylene, or tetrachloroethene. Tetrachloroethylene is the common. Tetrachloroethylene has been used in the past as a dry cleaning solvent. Okay, freons are chlorofluorocarbons, or CFCs. and these are refrigerants. Okay, among the most widely used were, okay, notice past tense there, trichlorofluoromethane and dichlorodifluoromethane. Okay, these were thought to be ideal substances. They were gases. They were very inert, and they were non-toxic, non-corrosive, and as uses in refrigerants, they worked very well. The problem was that when they got into the upper atmosphere, when they were exposed to really high energy ultraviolet light, okay, they formed free radicals, compounds that had an odd electron, and this ended up depleting some of the ozone layer. The ozone layer is something that we need in the stratosphere to protect us from high energy ultraviolet light. And so some of the alternatives that have been used include hydrofluorocarbons, HFCs. Okay, the advantage here is that these will break down before they get to the stratosphere, and also hydrochlorofluorocarbons. In some cases, even compounds like butane are used as refrigerants. Okay, in this chapter, we're going to demonstrate and concentrate on two types of reactions. The alkyl halide is a functional group and has a particular function. And the two main functions are what we call nucleophilic substitution, and the other one is called beta elimination. Okay, in general, substitution, okay, one functional group replaces another. Okay, that's all there is to that. And so here on top in red, we have the bromine being replaced by OCH2CH3 to give us an ether, and in the bottom reaction is an elimination, okay, where we end up with an alkene. Okay, notice that in elimination we increase the bond order. In a substitution, the bond order doesn't change. Everything's a single bond. It's a single bond in the product. Okay, in substitution, we're going to get a variety of different products depending on what nucleophile we use. In elimination, we'll get an alkene. Okay, so substitution and elimination. Okay, so we have some kind of a nucleophile. A nucleophile is an electron pair donor, also known as a Lewis base. And nucleophiles will have a lone pair of electrons that they can donate. In some cases, a nucleophile could be a pi bond from an alkene or alkyne. But in this chapter, we'll talk about nucleophiles that have a lone pair. In most cases, the nucleophiles will have a negative charge. Okay, there are some examples, such as water and alcohols, where the nucleophile has no charge. Okay, but there aren't any that have a positive charge. Okay, positive charge means a deficiency in electrons. If you're deficient in electrons, you're not going to be giving them away. Okay, so there's three parts, actually 4 parts in this reaction. Okay, we have the nucleophile here. We have the substrate, okay, which is going to be the alkyl halide. X is a halogen. So nucleophile, substrate, okay, this is our product. And then our halide ion, okay, Cl minus or Br minus or whatever it happens to be, is what's known as the leaving group. Okay, these are just a few of the many nucleophiles that we can use to carry out a substitution reaction. Okay, so here is our substrate. For example, this is CH3X, okay, where X is chlorine, bromine, or iodine. Okay, and then this is the nucleophile, the group that will replace that X. Okay, so we could use hydroxide, and when that replaces the X, we get an alcohol. If we use an alkoxide, we get an ether. Okay, SH minus, we get a thiol, we get a sulfide. We can also get a different alkyl halide. For example, we can take bromomethane and obtain iodomethane. Okay, we can form an amine salt using ammonia, also called an alkyl ammonium ion. Water can be a nucleophile, although it's a much weaker nucleophile than hydroxide. And then an alcohol can be a nucleophile. All right, there are two limiting mechanisms for substitution that we'll look at. Okay, the fundamental difference between them is the timing of the bond breaking and bond forming steps. Okay, over at one extreme, we have one that is known as SN2. Okay, and in an SN2, the two processes take place simultaneously. Okay, what two processes, bond forming and bond breaking, happen at the same time? All right, so S stands for substitution, N stands for nucleophilic, 2 stands for bimolecular. Okay, so there's 2 species that are involved in the rate determining step. And in an SN2, there's only 1 step, so that is the rate determining step. And then there's 2 molecules that make up the transition state, or 2 species that make up the transition state. Okay, not only is it bimolecular, but it is also kinetically second order. Okay, so this is the general rate law for a SN2 reaction. Okay, the rate is equal to some rate constant times the haloalkane concentration times the nucleophile concentration. Okay, so it's first order in each one of those, second order overall. Okay, so if we were to use the method of initial rates, and we, for example, we kept the haloalkane concentration constant, and we doubled the nucleophile concentration, that would double the rate. Okay, if we did it the other way, if we kept the nucleophile concentration constant and doubled the haloalkane concentration, that would double the rate. If we doubled both of them, that would quadruple the rate. Okay, so both reactants are involved in the transition state of the rate determining step. The nucleophile attacks the reactive center from the side opposite the leaving group. Okay, the key step is the reaction of a nucleophile and an electrophile to form a new covalent bond. Okay. Okay, so here is the mechanism showing the movement of electrons. So hydroxide attacks carbon from the backside. Okay, the side is electron deficient. So this bond forms, and then the carbon-bromine bond breaks at the same time. Okay, so the transition state would look something like this. It's a pentagonal bipyramid, or trigonal bipyramid, I guess it is. Trigonal bipyramid. Okay, this bond is forming, this bond is breaking. Okay, and okay, here are the products. Okay, note this highlighting here. Note the inversion of the reactive center. Okay, with bromomethane, you wouldn't be able to tell that, but if the bromine were on a chiral center, we would see complete inversion. Carbon is turned inside out like an umbrella in a strong windstorm. Okay, there's just one step in an SN2 reaction. There's one transition state, no reactive intermediates. Okay, and this is hydroxide with bromomethane. This one happens to be an exothermic reaction. All right, the other limiting mechanism, bond breaking between the carbon and the leaving group, is entirely completed before bond forming begins with the nucleophile. Okay, this mechanism is designated as SN1. Okay, where again, S means substitution, N means nucleophilic, 1 means unimolecular. Okay, so only one species, the alkyl halide, is involved in the rate determining step. And since only one species is involved in the rate determining step, this reaction is first order. And it's first order in haloalkane. It is zero order in nucleophile. Okay, so we can increase the concentration of nucleophile, has no effect on the rate. Okay, the rate depends only on the haloalkane concentration. All right, so instead of simultaneous bond forming and breaking, okay, the first step is the halide just leaves. It takes that pair of electrons with it, and since we've lost this pair of electrons from carbon, it now carries a plus charge. The electrons move toward the bromine, so it is now negative. And this is the slow step, the rate determining step. Okay, so this is a carbocation intermediate. And in this case, methanol is the solvent, and it's also the nucleophile. This first step is reversible, so bromide could come back to form the starting material. All right, so our carbocation is trigonal planar. We have an empty p orbital that's perpendicular to the plane of the ion. Methanol, which is the solvent and the nucleophile, could attack from either side, this way or this way. Okay, if the original alkyl halide was a chiral center, was on a chiral center, we would have equal probability of attacking from one way or the other. These are actually the same compound because they're superimposable mirror images. But if this carbon was originally chiral, we would actually get a racemic mixture. Okay, 50-50 of two enantiomers. Okay, so that's the second step. The third step is we're going to take away that extra proton, and our product in this case is an ether. Okay, notice the difference here between this diagram of the SN2, okay, remember the SN2 is one step, the SN1 is two steps. Okay, so the SN1 undergoes a bond breaking. That's the first slow step. We form the intermediates, the carbocation and the bromide. And then the second step is the fast step where the nucleophile attacks and we go on to products. Okay, so this one has an intermediate that has two transition states. Okay, so when an SN1 occurs from a secondary haloalkane, a secondary carbocation is formed, which is prone to rearrange to a more stable tertiary carbocation. Okay, we saw that in our addition reactions of alkenes. Okay, so for example, we have 2-bromo-3,3-dimethylbutane. The bromide leaves. We get a methyl shift. Okay, this methyl pulls out its electron pair and plants them on carbon number 2. And that takes us from a secondary to a more stable tertiary carbocation. Right, the next step is that the alcohol, which is the solvent, attacks. And then we have removal of this extra proton, and then this ether is our major product. All right, this is something I said just a moment ago, and that is for an SN1 reaction at a stereocenter, okay, we can recognize the stereocenter. It has 4 different atoms or groups attached. All right, so this is a stereocenter because this benzene ring is different from a benzene ring with a chlorine on it. All right, so the first step is ionization, and then methanol could attack from either side, and when that happens, we'll get a racemic mixture. We'll get both enantiomers in equal amounts. Okay, so next we're going to examine some of the experimental evidence on which these two mechanisms are based. And as we do, consider the following questions. What effect does the structure of the nucleophile have on the rate of the reaction? Okay, we really haven't discussed that yet. Secondly, what effect does the structure of the haloalkane have on the rate of the reaction? Okay. Third, what effect does the structure of the leaving group have on the rate of the reaction? And what is the role of the solvent? Okay, so these can all affect the type of mechanism and the rate of the reaction. All right, let's look at nucleophilicity or nucleophilic strength. This is actually a kinetic property. It's measured by the rate at which the nucleophile attacks a reference compound under a standard set of experimental conditions. For example, the rate at which a set of nucleophiles displaces bromide ion from bromoethane in ethanol at 25 degrees Celsius. Okay, in the next table, we'll look at some common nucleophiles and their relative nucleophilicities. Okay, so up here at the top, bromide, iodide, CH3S minus, RS minus, okay, all of these are the best nucleophiles. Okay, they'll react fastest with bromoethane. And we have moderate nucleophiles, and then Down here we have poor nucleophiles. These will react very slowly. Okay, notice that in general, charged nucleophiles are better than uncharged. These neutral species like ammonia and amines, they're fairly good nucleophiles, but generally not as good as these with the negative charge. Okay, so that's a listing of nucleophiles. Okay, so the better the nucleophile, the faster the reaction by SN2. Okay, let's look at the structure of the haloalkane next. SN1 reactions are governed by electronic factors, namely the relative stabilities of carbocation intermediates. Okay, so if we're going to form a tertiary carbocation, that will react fastest by SN1. If it's a methyl carbocation, that won't react at all. Okay, so that's electronic factors, how stable the carbocation is. SN2 reactions are going to be governed by something different, that is steric factors. Okay, namely the relative ease of approach of the nucleophile to the site of the reaction. Okay, in other words, the less crowded the haloalkane is, the faster the reaction will occur. All right, so methyl halides react the fastest. Okay, then primary, then secondary. Tertiary halides generally don't react at all by SN2. Okay, they're just way too crowded. Okay, so here's an illustration of steric factors. Okay, so here we have bromoethane. Compared to 2-bromo-2-methylpropane, which is a secondary halide. Okay, and what we can see here, especially from the space-filling model here, is that for bromoethane, backside of this carbon is less crowded than for the 2-bromo-2-methylpropane. Okay, in fact, for this one on the right, the backside of the carbon is actually too crowded for the nucleophile to attack. But it can easily attack the backside of bromoethane. Okay, so this figure shows the effect of electronic and steric factors in competition between SN1 and SN2 reactions of haloalkanes. Okay, so if we have a tertiary halide, okay, like 2-bromo-2-methylpropane, okay, that's going to be governed by electronic factors. That's going to be SN1 and never SN2. Okay, it's too crowded. Okay, at the other end, methyl and primary are going to be governed by SN2. And those carbocations are so unstable that they're not going to react by SN1. Okay, what about secondary halides? Okay, they could actually go either way. Okay, they're going to be pretty slow by SN2, but they can still undergo SN2 reactions. The leaving group makes a difference. It makes a difference in both types of mechanisms. Okay, the best leaving groups are, at least in this chapter that we'll talk about, are halides. Okay, iodide, bromide, and chloride. Okay, fluoride is not is actually not a very good leaving group because the carbon-fluorine bond is very strong. Okay, these strong bases, like OH minus, RO minus, NH2 minus, are such poor leaving groups that they are rarely, if ever, displaced in nucleophilic substitution reactions. Okay, so here, iodide's a very good leaving group, an excellent leaving group. Bromide and chloride are also good leaving groups. Water is a fairly good leaving group. These are all much better than any of these. Okay, so the greater the stability of the anion, the greater the strength of the conjugate acid. Okay, you may remember HI, HBr, HCl, those are all strong acids, so these are weak bases. Okay, over here on the other side, NH2 minus is a very strong base, so it's a really poor leaving group. All right, hydroxide ion, OH minus, is a poor leaving group. Okay. However, the OH group of an alcohol can be, that out of the way, can act as a leaving group, water, if the OH group is first protonated by an acid to form OH2+, okay, which is a better leaving group, namely water. Okay, so let's say we're trying to make we're trying to replace this OH with a chlorine. Okay, if we do that in sodium chloride and water, nothing will happen. Okay, the OH minus is such a poor leaving group that it's not going to be displaced. However, if we use HCl, there is first a acid-base reaction that occurs between the alcohol and the HCl. This picks up a proton, which gives us a much better leaving group, namely water. So oxygen now has a plus charge. This pair of electrons will move toward the oxygen. Okay, that leaves an empty spot here, a plus charge, a carbocation. All right, then chloride can attack. Okay, so hydroxide's a really poor leaving group. Water is a good leaving group. So we can carry this substitution out in hydrochloric acid solution. All right, this would be an SN1 reaction. Okay, first of all, we've got a tertiary substrate, and we form a carbocation intermediate. Okay, the solvent can make a difference. Okay, a protic solvent is one that contains an OH group and is a hydrogen bond donor. Okay, so these are examples of protic solvents. Liquid ammonia could also be a protic solvent. Okay, the NH bond can, NH3 can hydrogen bond. Okay, so water, formic acid, methanol, ethanol, acetic acid, these are all protic solvents. The OH group is a hydrogen bond donor. These solvents will favor SN1 reactions. Okay, the greater the polarity of the solvent, the easier it is to form carbocations in it, because both the carbocation and the negatively charged leaving group can be solvated. Okay, so among these, water is the best. Okay, so what that means is that, okay, the halide's going to leave. Okay, leaving an ion pair, and then both those ions are going to be separated separated and surrounded by solvent molecules, which means they're solvated. And that decreases the rate by which they'll come back together. Right, an aprotic solvent is a solvent that does not contain an OH group or an NH group, and is not a hydrogen bond donor. Aprotic solvents are going to favor SN2 reactions. Although the solvents at the top of the table are polar, formation of carbocations in them is more difficult than in protic solvents. Okay, so these are some examples of aprotic solvents. Okay, they lack the OH group. Okay, let me go back here. These are protic solvents. I've got an OH group. Okay, so these can accept hydrogen bonds, but they can't donate hydrogen bonds. Okay, so we've got dimethyl sulfoxide, acetone, dichloromethane, and diethyl ether. Okay, before we go on to the summary, let's say we have something like KCl, potassium chloride. Okay, when you dissolve potassium chloride in water, right, I'm going to use potassium iodide instead. When you dissolve this in water, potassium has a plus charge. The oxygens are electron rich. They're going to surround and solvate that potassium ion. The iodide will also get solvated. Okay, it'll be surrounded by solvent molecules. In this case, the electron deficient or partially positive hydrogens are going to be attracted to the negatively charged iodide. Okay, so those are solvated and separated. I'm going to go ahead and erase this. And the difference with an aprotic solvent, let's use acetone. Okay, I changed from KBr to Ki because potassium iodide is soluble in acetone. Right, so acetone molecules are going to surround the potassium ion. This. And each one of these has a large dipole moment. The oxygen is electron rich, has a high negative charge, so there's a strong attraction between these oxygens and the positive potassium ion. Okay, what about the iodide? Okay, it doesn't get solvated. And so it is much more free to move through the reaction mixture. And so the SN2 reaction with an iodide is going to be much faster in acetone than in water. Okay, it doesn't have to shake loose the solvent molecules before it attacks. Okay, so this is a summary. Okay, if we look at the type of haloalkane, okay, if it's a methyl halide, SN2 is favored, same way with the primary, and SN1 does not occur, okay, because the carbocation is so unstable. For a secondary, okay, I said earlier that could go either way. A big determining factor in which way it's going to go is the solvent. Okay, what we just talked about, protic versus aprotic. In a protic solvent with poor nucleophiles, maybe something like water or methanol, in a protic solvent, okay, that's going to favor the separation of ions, so that'll favor SN1. In an aprotic solvent, such as one of these, it will favor SN2. For a tertiary substrate, okay, SN2 does not occur, it's only SN1. And then the last point is that if the halogen is at a stereocenter, for SN2 we'll see complete inversion, for SN1 we'll see racemization. Okay, we'll see a pair of enantiomers form. Okay, so that is it for today, and we'll pick this up again on Wednesday.